Hi, I represent AXT. AXT was established in 1991 and originally started off as an X-ray tube manufacturer. We're now Australia's leading supplier of top-end scientific solutions, representing about 30 different international brands, supplying academia, research and industrial clients. So the logos that you see up here are the ones that cover the mining industry. We cover mining industry, material science, life science and non-destructive testing. There are two companies out there who have developed LIBS systems specifically for the mining industry. So there's SciAps, who do portable instruments. It's portable as a point-and-shoot instrument, and Emission, who use continuous LIBS scanning. They've got three products, which is a core scanner, an on-belt analyzer and a slurry analyzer. So what is LIBS? We heard Alex from BV talk about laser before, laser ICP-MS. Well, LIBS is laser-induced breakdown spectroscopy. And what that means is you use a laser to generate a plasma, from which you get a spectroscopic signal to get the elemental composition and the element identity and the composition. So a laser itself is an acronym, so often asked at quiz nights. Light amplification for the simulated emission of radiation. So a laser is essentially a beam of parallel light. So normally light goes from a light bulb in 6 directions, but with a laser it goes in one direction. So all that energy that's normally going out and around is focused into one parallel beam of light. And so it goes through a selection of mirrors, focusing lens which directs the entire energy of the laser onto a point of the sample. So whatever is present in the sample emits its own characteristic wavelength of radiation, goes into an optical spectrometer, which are then and a detector. So the thing about LIBS, or optical emission spectroscopy, is that you have a lot more. Every element has its own characteristic wavelength, but they have more wavelengths available to them than XRF. So XRF you are restricted to normally at most 2 wavelengths that you can analyse to give you the sensitivity that you need, whereas with LIBS there are quite often hundreds. The way it works is the laser approaches the target, it's typically within a few nanoseconds. So it's the focusing optics that focus the parallel beam of light into one particular point. The laser heats the target, so you can see in the image that the laser is penetrating the top of the sample. And then you get laser ablation occurring. So when laser ablation occurs, you get vapour, heating, fragmentation, atomization and ionization. They're the 2 key things that we're after, shielding and reheating. And then after a few microseconds, you get a plasma. Now, as this plasma breaks down, all the elements emit their characteristic wavelengths. So the relative detection limit is in the order of low ppm to high ppb. A few nanograms are ablated per pulse. And the absolute detection limit is in the order of a few femtograms. So every element has its own characteristic wavelengths, but more importantly, every mineral has its own characteristic fingerprint of those wavelengths. So LIBS can do every element on the periodic table. Some elements are more sensitive than others. Lighter elements are more sensitive than heavier elements. And there is a remaining crater at the end. So it's classified as a non-destructive technique, but it actually removes a little bit of the material. So the crater is typically in the order of 300 to 800 microns deep. The ablated mass is a few tens of a nanogram, and you can actually use it for depth profiling. So this is similar technology that's used on the Mars rover. So the Curiosity on the Mars rover has been operating since 2012. It was produced by a company called KenCam. In that time, it's produced 200,000 spectra. So from 2012 to now, that 200,000 spectra can actually be produced in a couple of minutes. And the technology has been so successful that they're launching a different model system called the SuperCam on the 2020 mission. So the Curiosity on the Mars rover is a standoff measurement, so can operate from a distance of up to 7 metres. You can see these 2 images here. One is before and one is an after image. These holes that you see are actually 500 microns across. This system is charged by a little nuclear reactor inside it, so it's not something that we can really take out into the field with us. the laser ablation systems work by, it's called dichroic optics. So the wavelength of the energies coming back from the elements travels the same light path as the original laser beam that's going out. So just because they're different wavelengths, some of the wavelengths will go through the optics and then others are refracted off the optics. And so the analytical device is actually the same as the laser generating device. So LIBS in 2018, it's really a good time for the convergence of technologies that enable LIBS to be used in the analytical realm. So lasers were conceptualized in the 1950s. It was patented in 1960. Nobel Prize awarded in 1964. So up until recently, they've only been used at one end for non-destructive methods and at the other extreme, destructive methods. So non-destructive uses of a laser are a speed camera, a surveyor's theodolite, a CD player, they use lasers. And at the other end of the extreme you have destructive techniques such as laser cutters, laser welders, and even defence forces are using directed energy weapons. And somewhere in the middle of those two extremes is this optical emission spectroscopy. So it's been through developments in miniaturisation, pulsed lasers, so instead of a laser operating continuously, they're pulse lasers, so you get this high peak to pulse power that enables a good ablation of material. Laser optics, laser fibres, optoelectronics, electronics and digital pulse processors with computing power, and also chemometric algorithms. So the chemometric algorithms enable a mineral identity to be inferred from the elemental concentrations. Benefits of LIBS are its optical emission, not X-ray. They cover a wide element range, the entire periodic table, and the light elements are more sensitive than the... you get very good sensitivity on the light elements. So elements that you can't get by XRF, you can get by LIBS, such as lithium, beryllium, boron, carbon, sodium, potassium and magnesium at low ppm levels. So potassium, magnesium you can get on XRF, sodium you can get on XRF if you have a laser. And the other benefit of LIBS is that it's great for microanalysis. So typically the laser diameter is in the order of microns, and typically it's a 50 micron spot size. So you can really get an indication of the variability of the elements in your sample. And also it's fast. So lasers will typically operate at somewhere between 50 hertz and 1,000 hertz, which means 50 analytical shots a second, right up to 1,000 analytical shots a second. There's two companies that have been developing LIBS specifically for the mining industry, and this is over the last couple of years. There's Emission, which is a Canadian-based company that have developed Emission Breakdown, which is a on-belt analyzer, continuously analysing at 1,000 analytical points a second. A slurry LIBS, which is a standoff measurement that can do liquids and also solids in liquids. And the Curiosity. The Curiosity is named after the Curiosity on Mars, but that's for core analysis at between 200 and 1,000 metres of core a day, depending on the resolution between the spot sizes that you want. But also the SciAps LIBS. SciAps is an American-based company. They've developed the SciAps Z300, which is specifically for geologists in the field. The founders of SciAps were the guys who invented the Innovex portable XRFs. They sold that to Olympus in 2011, and in that time, since then, they started working on the miniaturisation of the LIBS as a handheld instrument. They launched their first commercial model in 2015 for the alloy industry, whereas they honed the hardware for in those few years with the alloys. Now, alloys are a lot simpler than your standard mineral, and alloy will have from 1 to 6 elements. They tend to be homogeneous. The spectra are quite simple. It's a lot different to your standard non-homogeneous mineral sample. They've got two models, the Z300, which covers the wavelength range of 190 to 950 nanometres. They developed the spectrometer specifically so that you can get carbon at 193 nanometres, and then in the up to 950 nanometres you get elements like potassium, rubidium, cesium, and the more sensitive lithium line. They also have a Z200, which only has 2 spectrometers in it, which is a smaller system. You can still do elements that are unavailable on XRF, like sodium and lithium, but the lithium is not at its most sensitive line. We heard speakers from commercial labs talk about submitting samples and then getting an over-range result coming back. For a total technique, ideally we want to be able to analyse from, okay, ppb, but low ppm right up to high percentage levels. So that's quite a few orders of magnitude that the calibration curve has to cover. And because handheld LIBS is a total technique like handheld XRF, you have to account for the fact that it's a total method. You want to go from low ppb to high ppm. So SciAps have developed the calibration curves to be able to deal with this type of variable concentration range. So the calibrations have correction factors in them as a relative intensity ratio. The calibration curves can be 0 order, first or second degree polynomials, and you can also do split curves. So typically, like this is a lithium calibration curve. So the first part of the curve is on a different calibration, which is typical y equals mx plus b calibration curve. And then to account for the high concentration levels in, say, a pure spodumene sample, you get a first order polynomial curve. LIBS is more matrix sensitive than handheld XRF. The software, every instrument comes with its own PC-based software where you can easily tweak the calibrations that are in them. So they come with a standard geochem calibration which you can use as a semi-quantitative method, or if you want to make it a more quantitative method, you can tweak it with your own samples. The best samples to use are ones from your own deposit that you've had analysed by a reputable commercial laboratory. You know those samples will be matrix matched. If you're lucky enough to get a CRM that's matrix matched to that deposit, then yes, definitely put it in. Samples need to be presented as a pressed powder. Otherwise, the handheld LIBS system, it actually makes the sample puff up and you don't get such a good reading. SciAps have developed, the SciAps LIBS system, in order to be future-proof, they've developed on an Android operating system, and the functionality is via apps. So there's 3 apps for the Geoscientist. There's Geochem, which is standard point-and-shoot app, and again, that comes with custom calibrations for different matrix types. There's another app called Element Pro, which is a non-calibrated screening tool. So you zap your sample and it gives you the relative intensity of all the elements that are there. So it's a good way of picking up unusual elements that are present in your sample. And they also use the functionality of the microanalysis for heat maps. So with the 50 micron spot size, you want to be able to analyse quite a few different points on your sample to get a representative analysis of your sample. So here you can see an image of gold in pyrite. This is using the rastering power of LIBS, so it's a 16 by 16 grid pattern. And the colours indicate the intensity of the elements that are there. So gold in the middle, and then you get the relative intensity of all the other minerals that are present. And so basically that's the power of LIBS. LIBS is great for microanalysis. You can use it as a point-and-shoot technique for semi-quantitative analysis, or if you want to make your result more quantitative, you do, as we have heard for XRF, where you dry, pulverise, homogenise your sample. But otherwise, it's a great technique for indication of the elements that are in your sample, and it's field portable. If anyone wants to know more information about either SciAps or the L-emission continuous scanning systems, I'm available. Thank you.